welcome to this video. We're going to be looking at logic and just exploring a few of the basic things about logic and then discussing binary relations, which is particularly helpful in microeconomic theory. So a logical proposition is a statement that is either true or false. For example, your statement could be today is Wednesday, or that 2 plus 2 is equal to 5. And the idea is that this statement is true or the statement is false. And there's no middle ground, it's just true or it's false. And in mathematics and economics, we're particularly interested in finding insights into propositions and how they connect with each other. And we formalize these connections using logical operators that connect different propositions to each other. So actually everything relates to logic. You can think about Econ 1010, Introduction to Microeconomics, and how you study the law of demand, which says that as the price increases, the quantity demanded of a good decreases. So you can that is the connection of statements together. The price increasing, that's a statement that can be true or false. And then the quantity demanded of a good decreasing, again, that's a statement that's true or false. And having one imply the other is connecting these propositions using a logical operator. So actually, pretty much everything that we're doing is using logic, not so in your face as P implies Q, but behind the scenes, you can actually break it down into that. And yeah, having a rigorous understanding of what's going on in terms of the maths of logic can be quite helpful. So just a quick refresher on some notation that you should be familiar with. Negation is this sign here, which means that it's not that statement. And it's actually pretty important that we understand this notation because we use it frequently. Conjunction is and, essentially, where you connect two propositions being true at the same time together. Disjunction is or, so it's P or it's Q. Either one of those things being true will make the P or Q statement true. Implication, P implies Q, means that every time P is true, Q is true also. And then biconditional, P if and only if Q, means that P and Q are true at the same time or they're false at the same time. And it's stronger because not only does P implies Q, Q implies P as well. And we actually define these statements using truth tables. And a truth table is essentially laying out all of the states of the world. So P can be true or false. If there's only P in this world, then there's only two states of the world. And then the statement not P is going to be false when P is true and true when P is false. And you can map out all of the simple operations here and in the different states of the world when you can discuss when that statement connecting them is true or not. I think the only thing that's worth particularly focusing on is down in this corner here. First of all, logical equivalence. If a statement has the same truth values for every state of the world, it means that those statements are logically equivalent. So P as a statement is logically equivalent to not P, because not P has the same truth values in every state of the world. And we actually will use this in proof by contradiction, proof by contraposition, etc., by showing logical equivalence between different proof techniques, which is pretty cool. And then this one people often get caught up on, so I'll just say it again in this video. The actual definition of P implies Q is what is written in this table. This is the definition of this statement. And in this definition, when you don't have P and do have Q, the statement P implies Q is true. A lot of people wrestle with that logically because our English language will perhaps speak in a way that suggests maybe this isn't the case. But in terms of rigorous maths and logic, this is just the definition of P implies Q, are the truth values listed below. And you can think of it as having no evidence to suggest that this statement is not true because you don't have P, which means what does Q matter? This statement is about when you do have P. When you do have P, you have Q. So in this state of the world, when you don't have P, who cares what Q is? It doesn't matter. The statement is still true. Anyway, just accept that. And if you're struggling with it, remember that this is actually the definition of that symbol. Okay, last thing to just quickly look at here is that statements that are always true are called a tautology in logic. Statements that are always false is called a contradiction. And statements that can be true or false, depending on the states of the world, are contingent statements. I think there might be a bit more. Oh yeah, that last part just says logical equivalence when they have the same truth values in every state of the world. Okay, so that's just the introduction part. Now we can look at binary relations and a few important properties that relate to these binary relations. Okay, so what is a binary relation? Binary relation is connecting two different sets and then a relationship between them two, which is another set of a ordered couple of elements from these two sets. It's a very technical definition. And the idea is that inside your set G, you have the relationship from the order of the couple of X and Y. So X is your domain, Y is your codomain, G is your graph, and then your Cartesian product of X and Y, which is all of the elements X coupled with Y, every possible combination. You then pick out of those combinations which ones you want to include in your graph, and that creates the relationship between the two. This might sound pretty hectic and intense, but it's actually quite simple. If we look at some examples here, say your set X is 1, 2, 3, and your set Y is A, B, C. We can define our relationship focusing on the G such that 1 relates to A, 1 relates to B, 1 relates to C, 2 relates to A, and 3 relates to C, and this set is defining the relationship between them. So we have our domain X, our codomain Y, and our graph G, and these three things together actually generates a relation. And this is something that in microtheory we use a lot to talk about preference relations, but you can actually apply that to anything. You can have that as people as your sets X and Y, and then the relationship can be siblings with. And then G, your set, will have all the different people in the world who are siblings with each other. You can create whatever type of relationship that you want. And often we care about properties of that relationship and proving different connections of these properties to each other. Another example of a relationship is actually the unit circle. You could say two real numbers relate to each other if they are on the unit circle together. So the set of relations will come from any X and Y, where X squared plus Y squared is equal to 1. We say that X relates to Y if X comma Y is a part of G, or X capital G Y. And remember, the order matters here for tuples. Okay, another example, if we look at the preference relation, gold, bronze, and silver. I think a lot of people have an intuition as to which one of those metals is better than the other ones. And we can define our relationship as the preference relation, which is that gold relates to silver, silver relates to bronze, gold relates to gold, silver relates to silver, bronze relates to bronze. And really that's just saying bronze is better than both gold is better than both bronze and silver is better than bronze, and they're all equal with each other. In terms of micro preferences, you have the weak preference relationship, and then a lot of relationships that generate from that relationship. So the strict preference, X relates to Y, is defined as X being weakly preferred to Y and not Y being weakly preferred to X. Indifference being defined as both X and Y being weakly preferred to each other. Preference relation is rational if it's complete and transitive. What does that mean? So we'll just finish here with some definitions of relations that are often studied in maths and economics, and then a couple exercises as well. So let's just take a look at this list. Most of these you should have already heard before, but we'll refresh on them and maybe introduce a couple new ones. Reflexive, that is a relationship property where every element in your domain relates to itself. That's it. It relates to itself. Irreflexive is the complete opposite of that. Every element in the domain does not relate to itself. It's not saying that there exists some that doesn't relate to itself. It's saying that none of them do. Symmetric means that if x relates to y, then y relates to x. A great example of a symmetric relationship is a sibling relationship. If x is siblings with y, then we can infer from that that y is also siblings with x. Antisymmetric, if x relates to y and y relates to x, then x is equal to y. So an example of that could be the greater than or equal to relationship, because if two numbers are greater than or equal to each other, they must be the same number. Asymmetric means that if x relates to y, then y does not relate to x. An example off the top of my head could be the mother relationship. If you know that person X is the mother of person Y, then we can infer from that that person Y is not the mother of person X. Transitive, if X relates to Y and Y relates to Z, that implies that X relates to Z. Extremely important property. Complete, if you take any two elements in your domain, then either one relates to the other or the other one relates to the other one. X relates to Y, Y relates to X. Okay, so let's look at some exercises. Is the unit circle reflexive? So if we take any, let me just flash back up the unit circle as a definition and then we can talk about it. X, Y elements of the real numbers such that x squared plus y squared is equal to 1. So if we take any two numbers x, and also in this context, we're looking at this set x as being both the domain and the codomain. So if we take a real number, will that real number relate to itself? Well, no, because if you take the number 10, 10 and 10 together is not on the unit circle, so therefore it's not reflexive. Okay, what about symmetric? So if x relates to y, does y relate to x? So if we think about what the unit circle looks like, and we have our x and our y, if we have a point here with this y value and this x value, and then we switch it, it will be this wide will become this high, and then this high will become this y, which will be there. And essentially we get this mirroring along the line y is equal to x. And yeah, that will still be on the unit circle because x, y, if you have that on the unit circle, that means x squared plus y squared is equal to 1. And if you just swap x and y, it's still the same thing mathematically. So yes. Transitive. Okay, is it transitive? Let's think about that one. So 0, 1 will be this point up here. 1, 0 will be this point here. And then transitivity would create 1, 1, which is over here. And 1, 1 is not on the unit circle. It's got too long of a hypotenuse from the origin. So no. Our counterexample is so those ones are on the unit circle and this one is not. and then you have A, B, B, C, A, C as the connection. A relates to B, B relates to C, but A does not relate to C. Okay. Second exercise, prove that if R is irreflexive and transitive, then it is asymmetric. So to look at this one, we want to start off our proof here by letting R be irreflexive and transitive. And then from above, that means that this statement here is true and this statement here is true. And then we're trying to prove from those two things that we have asymmetric, which is here. We're trying to prove that this is true. So let's start off by establishing the premise of asymmetric, which is that x relates to y, and then see if we can infer from the other things that this is true. So let x relate to y. And we want to show that y does not relate to x. So we can even acknowledge that here in our answer. And to do this, we'll use a proof by contradiction. So because we're trying to show that it doesn't relate to this, let's assume that it does, and then show that that's impossible. So if y relates to x, we have x relates to y, and y relates to x, and transitivity, and we can put those together to imply that x relates to x as well. And because x is irreflexive, that's not allowed, and that'll give us our contradiction. So this is that written down. X relates to y, y relates to x, gives us x relates to x from transitivity, but irreflexive says that's not the case, and that's our contradiction. Therefore, it is not possible for y to relate to x, and therefore we have shown that if x relates to y, then y does not relate to x, and therefore we have shown that R is asymmetric. Okay, so that is our introduction to logic and relations together. Thank you.